Hello, and welcome to part one of the Resonant web series, where we explore impactful topics at the forefront of industry and academia, and which resonate at the interface of medicinal sciences, environmental technology, and digital innovation in healthcare. My name is Mike Miroshnikov, and today I have the honor of speaking to Timothy Manning-Swager, who is the John D. MacArthur Professor of Chemistry at MIT. Professor Swager is a pioneer and innovator in the field of applied polymer sciences. His group at MIT has spun off multiple successful companies and has developed polymers with applications in molecular electronics, including organic batteries, chemical sensors, and materials for environmental remediation. Famously, one of Professor Swager's polymers was adapted by the US military in the form of the FIDO explosive detector. FIDO utilizes a fluorescent material that can detect chemical vapors from TNT and has saved the lives of numerous military personnel in Iraq and beyond. Thank you so much for joining me today, Tim. Did I miss anything there?
No, it's my pleasure to be here, Mike, and thank you for that maybe overly generous introduction.
No worries. I was reading on the internet recently, and listen, people tell me that not everything I read on the internet is true. So I wanted to ask you personally. I know that you're from a small town in Montana, and I read that at one point you wanted to be a rancher. Is that true? And how did you end up falling in love with science and going from wanting to be a rancher to becoming an accomplished professor at MIT?
Well, it certainly wasn't a linear path. At some level, I really like physical labor. Everybody in my neighborhood has a snowblower with a driveway our size, and I like to shovel it by hand. I like so I like to mow the lawn. I like to do things. So I've always liked to use my hands and build things. And so when I was young, I worked on ranches for a number of years and was actually quite good at it. And the fact is, I ended up working for 5 years on my wife's uncle's ranch, and I thought I was pretty good at it, and land was cheap, and so I was planning on maybe starting to try and work and buy property on the side. My dad didn't like that. My dad was actually the town doctor, a very small town of 600. They called him Doc. He had an office, it was there before there was a hospital. And he didn't like that. So he really pressured me to go to college. So I went and initially, went to some agriculture classes. Those didn't really quite take. And in all honesty, my first year was a little bit of a wipeout. And I think it's a great country where you get to have a do-over in the United States. So I think we're really fortunate that way. Not everybody would be able to have that privilege. But after that year, I came back, worked at the ranch a little bit, and I thought, well, maybe I didn't give it a fair shot. And I just decided, what should I do? Well, I always thought chemistry was kind of neat. You build things, build molecules. Maybe I'll try that. And if I get good enough at it, I thought it would be fun. So I went back to college, a different university, went to Montana State University where I got my degree, and didn't look back.
Yeah, thanks for sharing. And if there's anything that anybody in chemistry can tell you, is that it is a lot of physical labor. And I think the first time when I was an undergraduate and I had to spend 9 hours on a Saturday doing a column by hand, I realized the manual labor that was involved. And at one point, maybe I thought I wasn't built for it either. But like you said, we all get a second chance, and look where we are now. So I think everything turned out for the best.
Mm-hmm.
So let's get to the reason why we had you on here today. You want to talk a little bit about N-nitrosamines and their impact on the environment. Me coming from a pharmaceutical background, this is a big issue, right? Because these things are everywhere, and you could take a pharmacologically active reagent, having a reactive secondary amine, and then it reacts with a nitrite, which is a very common curing agent, preservative, excipient in pharmaceuticals. And under the right conditions, these things can react and form a carcinogenic agent. But beyond pharmaceuticals, you say that we should be concerned about these things in the environment, and you want to show us why. Is that correct?
Yes, yes, I'd love to do that. And I have some slides here if that would be okay to present.
Yes. Please take it away. I'd love to hear what you have to say on the topic.
Okay. Just want to make sure. Are you seeing one or two screens?
I'm seeing one.
One. Okay, so you're seeing the right view. That's good. Okay, great. So first, let me say that nitrosamines are, as you mentioned, very toxic. They're carcinogenic. I'll go into that, and for some reasons I'll also go into. They are of interest to public health, and in particular, there is a site in Massachusetts where they've become particularly problematic that is become a Superfund site, and we have a program at MIT that's addressing the health risks and the monitoring of nitrosamines at that site. And so we have something called the MIT Superfund Research Program, which is headed by my colleague Bevan Engelward, and I'm privileged to be a member of that, and it's a federally funded program. So nitrosamines, what we have here is we have molecule, nitrosamine that has a nitroso and the amine parts. There are two different types of nitrogens here, and that's where maybe some of the pharmaceuticals have developed. That when you have nitrogen in different environments, sometimes they can get together and start forming these compounds. And one of them is technically oxidized. That's the case where we have the nitrogen that has the oxygen on it, and this is what we call an oxidized nitrogen. This one, the R groups here are carbons, which we would say is not oxidized. And so those are two different types of nitrogens. Now, it turns out that there are electrons on these molecules, so you don't always show them. It's a chemistry shorthand. But what they do is they create an electric field, a dipole, associated with these groups. So this molecular fragment is essentially like a little electric, charge here, a plus and a minus charge, minus being the charge of electron and plus being the charge of absence of electron or a proton. And so these are nice, very polar molecules. Now, in reality, they don't really look like one or the other. They kind of look somewhere in between. So this is essentially how we understand them chemically. So that's just the basics of nitrosamines. But as you say, where do they come from? Well, a lot of times they come from industrial sources. There's a solvent called dimethylformamide that's used very widely, and it tends to essentially liberate the amine portion of those nitrosamines, which in presence of other types of nitrogen species can create nitrosamines. And this is a very particular one. These little lines here represent just methyl groups. And so this is nitrosodimethylamine, or NDMA. There's different ways of naming it, but we really refer to it from here on as NDMA. And also, instead of just simple nitro groups, you can have all sorts of different amines which can enter into the ecosystem, either sometimes naturally or through industrial processes, that in the process of doing water treatment, and we usually treat water by chlorinating it to kill essentially bacteria so we don't get sick, but that same chlorination can give rise to chemistry that again forms these nitrosamines. So even these amines themselves are not carcinogenic, but after a water treatment, they can generate carcinogens. And so there's all sorts of different precursors, as I mentioned. They can be naturally occurring as well. Now, the good thing about nitrosamines, and I'll come to this a little bit later, is they tend to break down than sunlight. So that's good. Otherwise, they would be all over the place. So light is bad. It tends to break them down, and sometimes they biodegrade. We often ingest some nitrosamines, daily. They're in cured meats, and they're also in beer. And we do ingest them, and it's not, at a certain level, it's not a problem, and they may not be the worst type of nitrosamines. They may not be that dimethyl nitrosamine or NDMA. They'll be different types. Now, you mentioned there are other types of nitrosamines. Cigarette smoke contains them. There were some contaminations and medications. Those have been, I think, dealt with by and large. People now recognize that, but workplace exposure is another case, and even our digestive system can create some of these nitrosamines. Now, they have been known to be carcinogenic for a long time. Actually, many years ago, they were even used as solvents, and people started getting sick. But they've been around in use in industry for many years, and it wasn't until modern times that people recognized just how bad they were. So why are we interested in nitrosamines in Massachusetts? Well, I'm in Cambridge here, which is where MIT is, which is just right across the river from downtown Boston. But still in a larger metro area, there's a town called Wilmington. It's shown right here on this map, and you can see Massachusetts is a fairly small state, so it looks like it's a long ways away. But when you think about how small Massachusetts is, it's really not that far. It's basically really in suburban Boston area. Now, Wilmington was the site right next on its border with Woburn, was a site where there was chemical manufacturing for many years. There's a whole series of different companies that occupied this particular site, shown in red, most recent being Olin. And over time, there was, very large scale manufacturing going on. And what people did back then, which was, I think right now, just absurd to most of us, is they would take their chemical waste and they would put them out in these ponds. You see here is a photo from 1967. They're like little lakes. These are chemical waste dumps where people were dumping things into these open air ponds. And this waste stream then essentially entered the environment. It got away. It wasn't. They thought that it was be contained. Obviously, that was more wishful thinking at best. And it started generating this NDMA in the groundwater, which then ended up in people's tap water. And this really became a very big deal, because there was a childhood cancer cluster broke out in this area where it was statistically very high cancer rate for children with cancer to get cancer. So there was something in the environment, and a number of community activists basically identified this and came and figured out that it was NDMA. So this was really the community members that really that were the heroes in figuring this out and saving their children. And they found that in particular, there were a number of municipal wells here that were being contaminated, that were, a significant distance away from this Olin chemical site, but they had MDMA in their groundwater. And so things went forward. The chemical site became a Superfund site in 2006. All the wells were switched off. They got different types of of water to the citizens, and so things have improved, but there is still a major toxic waste cleanup operation underway. So here is kind of a more modern picture of the site. This is one of those ponds that's being covered here, and there were 25 million gallons of what is called dense aqueous phase liquid, or DAPL, in the ground. And that's just basically water mixed with chemicals. And so this is 25 million gallons in the ground like that is a non-trivial thing to deal with. And so this is something that's very much ongoing. Now, you might be wondering why NDMA is so bad for you. And it really is about its metabolism in our body. So this is NDMA, and now I'm showing those methyl groups, not just lines. Those are these red CH3 groups here are methyl groups. And what happens is our body has these enzymes like your cytochrome P450, which tend to oxidize organic molecules, break them down so we can basically excrete them in our urine. And when NDMA gets broken down, however, it loses one of these methyl groups and it becomes this charged species here. So there's a positive charge here. And this is essentially these two nitrogens together want to become nitrogen gas. And so this becomes a very powerful alkylating agent. That is, it tends to transfer this methyl group to other reactive species. And in particular, in your DNA, adenine is one of the nuclear bases in your DNA, tends to react with this and it gets methylated. And this causes mutations in your DNA. And these particular mutations can essentially give rise to cancer. Okay, not all of them. Your body is very good at correcting these things. But if you get enough of these and they keep trying, they succeed in forming cancer. So this is the reason we have the Superfund site at MIT, and a big portion of our research goes towards understanding the toxicity, what the levels are, what the implications are, how you might actually deal with these cancers or prevent this cancer. And so there are many things going like that on like that in the biological front. My group is more, as you mentioned, is more on the materials side and the analytical science. And so we tend to work more on essentially, the collection of it, the concentration, detection, and the chemistry of this group of MDMA. And here are some of my coworkers that have worked on this, Jessica Haushin and Ruchan. They've all contributed different ways, and I'll actually mention their different work. And in particular, Jessica wrote, which I think is one of the authoritative reviews on the chemistry of nitrosamines, and which we published fairly recently. So how do you go about detecting NDMA? Well, you have to essentially extract it from the water. Now, remember I told you how it had these little electric fields associated with it. It really likes water. So you have a hard time getting it out of the water, but you have to extract it, you have to concentrate it, you have to separate it, and you have to use fairly complicated equipment to quantitate how much is there. It's something you cannot do in the field. It requires a very sophisticated laboratory. And so what my group tends to do is to try and figure out ways that we can develop methods that can be used in simpler situations, essentially even out in the field, something you could do with minimal equipment. That's our goal. And how we do that is through using innovations in chemistry and materials. And one innovation we have is ways of just binding this molecule. So here I draw this MDMA again. I show kind of a three-dimensional rendering of it here. And what we've done in this case is we developed these other molecules that essentially look like little bowls. But on the inside of the bowl, there's this tungsten atom, which tends to want to interact with negatively charged groups like the oxygen. Remember, the dipole on that, or the electric field across this molecule, put a negative charge on that oxygen. And so these molecules behave as what we call receptors. They tend to be uniquely disposed towards binding things like this that have this kind of geometry. And what I'm showing over here on the right are two X-ray crystal structures. So we can use methods in our department to basically determine at atomic precision structures of different complexes. And so what we're seeing here is this bowl-like molecule that has NDMA parked in its cavity. We have two different types of them, this one having a more elaborated structure on the far right. And so we make use of these different groups to bind the nitrosamines. And there are a number of ways that we've used this to detect and to concentrate them. One I thought that would be kind of interesting to tell you about is how we can basically take these materials and put them as an overcoating on essentially something that you might think of, it looks like a tuning fork, something that is a resonating structure. We use quartz, which is the same sort of frequency counting material that is used to keep time in your watches. And what you do is you basically put this material over the top of a metal electrode on that quartz. And when the quartz is vibrating, if you absorb more molecules to it, because in this case, our molecules are going to want to bind inside the cavity of this polymer or interact in a receptor form, what you're going to do is essentially dampen that frequency. So just like you have a tuning fork, if you basically put your finger on it, it will dampen it. And the same thing happens here. But it's done at a very, very exquisite level of sensitivity where it can detect very small amounts of mass. So this is a way you can use these receptors to detect MDMA by just looking at changes in the frequency of these types of little resonators, or these little tuning forks. Now, other ways that we detect NDMA is sometimes we also interact them with metals that tend to give off light. These are molecules that I'm showing here that are all emitters. That is, if you shine light on them, they emit another photon, so they fluoresce. And their fluorescence is very dependent on NDMA. In the absence of NDMA, they fluoresce. In the presence of MDMA, they quit fluorescing. So these are ways of using essentially optical indicators that can detect MDMA. I just want to tell you about one last method that we use here, and it has to do with the fact that, as you recall, I mentioned that MDMA or nitrosamines in general tend to break down in light. They tend, when you excite them, you give them light, which is we show that as H nu here. So when a photon is absorbed by this, it creates a lot of energy in this molecule, and this molecule can essentially break apart. And where it likes to break apart is between these two nitrogen bonds, as shown here. So it tends to fall apart and fragment, and it does a few other things, which sometimes give rise to other species before they fragment. But nevertheless, it tends to fragment. And we've used this method now to create colorimetric assays that work out in sunlight. So here's Jessica holding up her sample, and she outside our chemistry building at MIT, and she used light, and in 5 minutes, just in sunlight, this reagent she put inside there with the molecule, with the MDMA, basically changed color. It was colorless to begin with. It turned yellow. And then we can further enhance that color by binding it different metal ions. I can't tell you the specific chemistry right now because we haven't published this and we don't want to disclose it just yet, but this is something that we hope can be used to make a field assay. Now, there's always a human side to all these stories, and in fact is when you do research at MIT, one of the things that we benefit from is just having an outstanding group of coworkers. Here you can see them all dressed in their finery at one of a party we had recently. But what I want to do is highlight the people that I talked about that did this work: Jessica, Ruchan, and Haoshen. Haoshen did the fluorescent things. Ruchan actually made the receptor and did that quartz crystal microbalance work. And they're the special people that really make things happen. Once upon a time, I worked in the lab. I haven't worked in the lab for some time. I'm basically, the director of the laboratory. Our laboratory runs like a small business work, but I'm kind of the CTO, CEO, HR, and you name it. But we function really quite well together and are always up for the next challenge. So with that, I think I can stop sharing and answer any more questions you might have, Mike.
Thank you for sharing that, Tim, and thank you to Jessica, Ruchan, and Haoshen for their contributions. Really, really interesting work. Um, I do have a few follow-up questions for you. And so, people might, hear about nitrosamines on the news, and, they might hear this talk from you and they might panic, right? They might say, oh my God, these nitrosamines are in the water. I'm going to be harmed in some way. So my question is, given that you said that they decompose under sunlight, how significant is the threat, for the average person to be harmed by this? Can they be found in appreciable quantity in the average, tap water? And can somebody potentially, be poisoned by this if they, for example, don't dispose of a tobacco product properly, or if they flush a pharmaceutical reagent, down the toilet, for example? And is there something that can be done in the form of storage that can, prevent these compounds from getting into the environment?
Yeah, well, so you're right. I mean, we shouldn't panic. They're, you know, just being around automobile exhaust is not good for you either, right? And so,
Yeah.
but we all have to be around that. And it's usually the kind of thing that too much of anything is usually not good for you. So if you eat cured meats every day, all day, that's not good for you. It's not good for your digestive system. They have lots of nitrosamines. You drink too much beer, that's not obviously not good for you. Smoking cigarettes, we all know about that. So I think that there are ways to limit our intake, and I do. And one thing to bear in mind is our bodies are resilient. So I mentioned how your body will make this reactive group that can alkylate your DNA, but our DNA repair enzymes are very good at fixing these things. So, most of the time they fix it. Every now and then there's a special case where some of the bases get where it can copy over and it can avoid the repair, and that can give rise to a mutation, which, if it creates viable cells, creates cancer. So but that's still a rare event. That's still a rare event, and that's why we, live as long as we do. Is our bodies are very good at fixing things. Um, with regard to, I think we do have some cleanup from errors in the past, and in the nitrosamines. Another area that people probably have heard about is PFAS chemicals. Are something else that's in our water system that we have to take care of. We got to clean it up. And I think the big thing for us as a society going forward is to quit making these messes, right? That we need to kind of quit doing that. You mentioned not flushing pharmaceuticals down the toilet. That's also something that we shouldn't do, just because they get into the environment and they can start doing things. And not just even nitrosamines. There are things called endocrine disruptors that can cause other biological effects. So I think if we just all start, being a little bit more careful with our environment and how we dispose of things, and keep our regulations such that we don't try and essentially save a buck and make a mess for the future, that's going to be really important going forward.
Yeah, and I agree. We all have to do our part, to help the environment. And I can say from personal experience, this is a big deal for us in pharmaceuticals, and it's a big deal for the FDA also. So nowadays, whenever we make a new compound and there's a potential risk, we have to assess that risk. We have to stress test our compounds, see what are the chances that it could form one of these harmful nitrosamines. And if there is, how can we modify our packaging and how can we modify our chemical processes to prevent these compounds from forming and, essentially negating what our medicines are trying to do. We want our medicines to be sustainable. We don't want them to harm the people that we're trying to help. And so, I'm happy that we can each contribute from our, respective industries, both in pharma and academia.
Yeah.
Um,
No, I think it was one of these, a very unexpected thing to have these crop up in the pharmaceuticals. But now the good thing is now we know about it and they know how to look for it.
Absolutely. The second question I have for you is a little bit more technical. So I was reading a few of your papers, and I know this is not the only polymer that you've developed for nitrosamine remediation. You also have another polymer, and of course, I don't really have the structure on me right now, but I could best describe it as pyrrole, which you polymerized and adsorbed onto a cyclodextrin matrix, and then you interdispersed it into oil to make a colloidal particle. So these are two structurally and conceptually different type of polymers. And so I'm just wondering, how did you conceptualize this, dichotomy of two different materials, and what might be the application of one versus another in terms of, is there a better, forum to apply one of these compounds? Would they be more useful in a certain situation compared to another one?
Yeah, so Mike, I often get asked about how did you come up with that idea or whatever. And I think you're in an environment and things shape you and you're searching for something and I don't want to I would liken it this way, not maybe tongue in cheek, to an artist. How do they get their inspiration to do something? They're thinking about it, and then somehow it just comes to them, right? And so I think really in science, it's not so different than artistry, where you're putting different things together in the moment, seeing things. And so now the parole system that you talk about is something that we comes out of a kind of different, branch of my research group where we work with complex emulsions, things where we disperse particles in fluid state in water. We have ways of making sensors. We've actually commercialized some of those in bacterial detection in a startup for food pathogen detection. And so we have a lot of experience with that. And one of the things about the polypyrrole is it's a responsive polymer. We found that it could basically, through stimulating it, you can make these particles expand and contract and have different properties. So we thought that we could use those as things you could disperse into a liquid. They would absorb something, you collect them, they just fall to the bottom, they're denser than water. And remove the water, and then if you switch them, you just treat them very simply, you switch them, they'll release everything, and then you can use them again. So they're kind of like, it's the idea of, think of it like a sponge, where we were trying to make something that looks like a sponge, where you can wipe up something and then wring it out and have it wipe up again. And this is chemically essentially the equivalent of what we were doing there. And the cyclodextrins you mentioned are the little pores in our sponge that are molecular size and give it molecular specificity.
So when comparing those two polymers, you would say that one of them can be more used for like a physical separation, while maybe the other one can be used or applied, for testing, perhaps. Can you apply one of them in sort of like a test strip?
Yeah, so yeah, the one I showed you, the stuff I showed today is best suited for sensing. And one thing about sensing, you need very small amounts of the sensing material. I didn't mention that, but just you're detecting small amounts of the molecule. It takes also equally small amounts of your sensing material. So it's not unusual for us to make a sensor out of a microgram of material. So that's if you have 1 gram, which is basically, like the tip of my thumb would be less than a gram or around a gram. You basically have that and you can make 1 million sensors from it. So we have those molecules I showed you were not entirely trivial to produce. So they're not cheap molecules, but the pyrrole and the cyclodextrins are things that are commodity chemicals. And so we could make those. Imagine cleaning up MDMA or even cleaning up an oil slick or some other environmental disaster. If you could bring something like this and recycle it quickly and essentially get all the chemicals out, that would be a good use of it.
Thank you. Thank you so much for that again. I want to touch very quickly on what you said about the kind of creative process, because that actually really struck me. I remember reading somewhere that Einstein was actually a talented pianist, and not a lot of people know that about him. And what he said is, as a scientist, you also have to be somewhat of an artist. And a lot of people, perceive scientists as somebody, people who just crunch the numbers and do some calculations on a whiteboard and come up with an idea. But you also have to have some imagination to do this, and I like that you mentioned that.
Yeah, I do, and it's also, I don't think you can stereotype scientists. It's like we have parties with my research group over at my house, and we have a upright piano, and there's usually about they'll get going, and three or four of them will go, and they'll sight read music firsthand beautifully, play like a concert pianist. There are a number of them can do that. I've had a couple that play the cello, and people that have a painting in my dining room that was done by a postdoc that everybody looks at is like amazing. And she told me it took her a month. She did it after she left the group and sent it to me as an appreciation gift. But yeah, no, I've had artistry runs pretty deep in scientists, and I think that hopefully people can look at us as having more dimensions than they might think we do.
Yeah, for sure. And I like to, think of it that way. And you can't move forward with something, monumental and not incremental in terms of science if you don't have a little bit of an imagination, or else you're just kind of modifying what somebody else did. And the last thing that I kind of want to ask you is, I did notice that with your metallocalyx-arene polymer, you synthesized, or your group synthesized, this material using the Grubbs third generation catalyst to kind of do the olefin metathesis and create this compound. I know that you are the student of the late Nobel laureate Robert Grubbs, of course. So I want to ask you, do you find yourself often going back to your roots in research to conceptualize and develop new research methods?
Well, it's I think we're all when we think about our lives, we're products of our environment, right? And in your childhood environment as a scientist, I had, one of my initial very big growth phase was working as a PhD student under Bob Grubbs, who was, he was like a second father to me. He was a really, really kind and great man. And he gave, he had a lot of creativity too. He had kind of, we call them crazy ideas usually. You use the same thing. All scientists say, I got a new crazy idea, and crazy idea usually means that if it works, it'll be really good. But chances are it might not work, right? And so I got a lot of that inspiration from him, and just it was okay to fail too. I mean, if things didn't work out, he was okay with it, and there's no fear of failure. And so I think that environment helped me a lot. I don't know. It's hard to kind of piece together who I am and where I came from, and I think we all struggle with that when we think about our lives. But I certainly did get a big imprint from Bob Grubbs, and I think many other people did. He was really really known to be a genuinely really nice person.
Yeah, and what you said about having, this crazy idea, I think that, I come from a traditional organic synthesis background as well. And I didn't really decide that I'm going to go for this PhD, for example, this arduous, long journey that has a lot of, trials and tribulations, as any graduate student will tell you, until I was inspired by this crazy idea of using organic molecules, in electronics. And I know you do a lot of organic batteries, and I did my thesis on organic materials for batteries as well. And we don't know whether we're going to use organic molecules as electrodes. There's plenty of organics in electrolytes and separators, right? But are we going to use, quinones or, some of these electrophilic compounds for electrodes? We don't know, but it's an idea worth pursuing. And, if you think about it in terms of sustainability and helping the environment, it's worth getting passionate about. And that's kind of how I felt as well. And I think me and you definitely relate on that issue, in which we find something that might sound a little bit crazy, but we go for it, and that's what keeps us going, right?
Yeah, absolutely.
Yeah, and so that's really all the questions I have for you. And before we sign off, I just want to ask, is there anything else you would like to add? Is there anything that students should know about your lab and how they could potentially contribute to the super fund? Yeah, this is your chance.
So as professors, we're always on the lookout for talent. But there's lots. First of all, I would say there are lots of different labs, lots of different ways to contribute. And I just like people to follow their passion. What's important is to do something meaningful in life. And if all of us try and leave this world a little bit better than we found it, future's going to be real good.
Yeah, thank you, Tim. I just want to give you another big thank you for your time and for joining me. And I hope our message finds the right people and inspires the next generation.